We're going to do some problems now involving kinematics formulas that require constant acceleration. So in order to do that, we're going to look at how these formulas are derived. Now, because acceleration is going to be constant, we're going to start with acceleration, which we know is the derivative of velocity with respect to time. So we'll start with dv dt equals a. Now what we're going to do is take the antiderivative of both sides. So the antiderivative of dv dt would be v, and the antiderivative of a will be at plus c. So we've increased the power of t to 1, and we've added a constant. But when t is 0, the velocity will be c. We're going to call that the initial velocity. So we obtain v equals u plus at. So that's our first formula. Now also recall that velocity is the derivative of position with respect to time. So dx dt is going to equal u plus at. The antiderivative of both sides gives x equals ut plus at squared over 2 plus a constant which we'll call d. And what we're going to do is say that when t is 0, x, the position, will be d. So that's the initial position. Now recall that the final position x minus d is also known as displacement. So substituting, or rather rearranging, we've got x minus d equals ut plus a half at squared. So I'm going to replace x minus d with s for displacement. Okay, so what we get is s equals ut plus a half at squared. So that's our second formula. Now if we substitute a rearrangement of that first formula, that is v equals u plus at, what we do is rearrange to make t the subject, v minus u over a. If we sub that into our displacement formula, we can obtain, I'll just go straight into the result, we can obtain the result v squared equals u squared plus 2as. So that's our third formula, and that formula is one we'd use when we know the initial velocity and final velocity and perhaps the displacement, but we want to find the acceleration, or when we know any of those three variables and we want to find the fourth. And that's the general rule we use for all these formulas. So the first one, for example, you can find time, acceleration, initial velocity or final velocity as long as you have the other three. And notice down here we've got a displacement formula, acceleration and time. So this is a good one to say find the time for a given acceleration, initial velocity and displacement. In any case, let's just go on. We can then use that result, so rather we can also say that the displacement travelled is the average velocity times time. So we can obtain another formula which is displacement is the average or half of u plus v times t, and that's our fourth result. So you'll not be asked to derive these four formulae, but you must be able to choose which is appropriate to use depending on the conditions of the problems that you're being given. So we'll just summarise what these formulas are. We've got v equals u plus at, where v is final velocity, u is initial velocity, A is acceleration and t is time. We have displacement s equals ut plus a half at squared. We have v squared equals u squared plus 2as. And we have s is a half of u plus v times t. Let's have a look at a problem now. We've got a body moving in a straight line with a uniform initial velocity. It's travelling with uniform acceleration at an initial velocity. Initial velocity u is 12 meters per second. And after 5 seconds, so I'm going to write t for time there, its velocity is 20. So that's v, the final velocity. First thing is to find the acceleration. So we're going to use v equals u plus at. So we substitute in those values and we get 20 equals 12 plus 5a. 5a equals 8. So a equals, acceleration is 8 over 5 or 1.6 meters per second squared. The next one, we want to find the distance travelled in this time. So we use the displacement formula, s equals ut plus a half at squared. So we know our initial velocity is 12, time is 5, half of the acceleration we just found times time squared, and that comes to 80 meters, so our displacement is 80 meters. Part 3, or Part C, the time taken to travel a distance of 200 meters. So let's use our displacement formula, s equals ut plus a half at squared, and we'll place s equal to 200, the displacement. We know our initial velocity is 12, but we don't know the time at which this displacement occurs, so we'll just leave that as t. We'll have half our acceleration, 8 over 5 as before, and again we don't know t. What I'm going to do there is to simplify that a bit. So 200 is 12t plus 4/5 of t squared. I'm going to times the entire equation by 5 to get rid of that fraction. And then I'm going to divide it by 4. And then rearrange it to get a quadratic. T squared plus 15t minus 250 equals 0. I can factorise that into t plus 25 times t minus 10 is 0. So t equals 10. We're not going to entertain the possibility of a time of negative 25, so we'll discard that solution. Now it's your turn to try a few problems yourself by doing some problems from exercise 19C from the text, and I would have attempt all of them.